take a look at each of these terms in order. We're going to use, a couple of times, we're going to use a particular trick. And the reason for using the trick is, again, that it allows us to sort of point up the overall behavior of the system. It certainly does, it's not obvious why we should do this, having the expression written out for us. And I think, I do have dB prime. Okay. And the trick that we're going to use a couple of times is this. It's actually just integration by parts. That integral is that's a prime. And yeah, that's it. The other term in the so-called integration by parts was we took the derivative of a constant. So we integrated by parts 1 times j. Okay? Why did we bother doing this? Well, we bothered doing this because this allows us to use the continuity equation, which is that divergence of j plus d rho dt must be equal to 0. That's the total charge in the system. Okay? So it allows us to take this j in here and turn it into a rate of charge, a rate of flow of charge. And because I had previously expressed the charge in this volume of the system as an oscillating exponential, that means that this derivative d rho dt is minus I omega rho. Okay, so what we're going to do first is look at this term in the expansion. So just that first term. And we use that trick, that series of tricks over there for the first term. So here we go down here. Oh. Magic has occurred for the first term down here. E-I-K-R over R. Integral now. This thing is now R prime, barring minus signs that I have probably dropped like crazy here. Rho d cubed, rather d, v prime. Let's see. Here, I have taken the time dependence into account. See, I had d rho dt here. I've taken the time dependence into account here with the I omega. I took the derivative already of the e to the I omega t. Okay? This term here, if you'll remember from way back when, is the dipole moment of the distribution.
Where did the C go?
Oh.
Is that from C row because it's J? No. So it dropped because of C row because of J.
Wait. Well, I've got a C here. CR rho. I don't think I had a C there. I think there is a C here. But I will qualify my answer with a P through the equal sign.
How much use have we gotten out of inventing that?
I've gotten quite a bit of use out of it. like it everywhere here at least. This is the dipole moment. So this is I screwed something up here. Oh, yeah, no, I don't. Omega over c is k. So minus phi k dipole moment e to the I k r over r for an oscillating charge.
That's just the first term of the extension, right?
That's just the first term in the expansion.
Okay.
So the actual fields that come out of that, I think that I have probably erased the forms. That's the vector potential. Now I want the fields from that vector potential. I'm going to use this trick again, but I'm going to erase it and just remind you that I'm using it again. That the magnetic field comes out to k squared. Oops, r hat cross p e to the I k r over r, and distributing the derivatives. Distributing is the wrong word. It's product rule. Gives me two terms. And that magnetic field then is always perpendicular to the vector between the source and the observation point. All right, so something's oscillating over here, and the magnetic field is going to be oscillating at right angles to the viewing direction. Okay, that makes sense. That's good. And it drops off this 1 over r. It's a dipole field, oscillating field is dropping off this 1 over r. The overall magnitude drops off as 1 over r. There is an additional term here that's out of phase. And I probably don't want to say anything else about it. I don't think. Yeah, I will say this. In Ohanian, actually, he does the derivation where he includes the explicit time dependence. What I've done is I assumed that everything oscillates as e to the I omega t, right? Whereas Ohanian did not make that assumption. And so he included the derivatives throughout, and there's a neat consequence that comes out of that. So I'll just write down the notation that Ohanian had, which is that this is minus 1 over c squared r cross. Now, there's a little bit of a tricky notation here. All right. We're going to evaluate the second derivative of the second time derivative of the dipole moment at time t equals r over c. Okay, so the brackets are going to say we're going to be making our evaluation at a particular retarded time. And the magnetic field in this case comes out to be the second derivative of the dipole. Right. This is compact, but the arithmetic to get here is more complicated than the arithmetic that I used to get there. Okay. And the electric field then, see, if we're dealing with currents, then the magnetic field is what we normally calculate first, and then we calculate the electric field from the magnetic field. I over k curl of B would be the electric field. And that's going to have multiple terms. I won't write it out right now. We've got the magnetic field for the radiating dipole. But I will tell you that what can happen here, because I've got these two terms that are out of phase with one another, is that the electric field does not have to be entirely along the perpendicular to the propagation direction. It has transverse and longitudinal components. In the far field are much, much greater than lambda and A in the problem. Then my magnetic field, let me erase the electric field right here for the moment. Far field, yeah. B is equal to K squared R cross P e to the I K R over, let's see, does that work out? K squared, yes, that's it. I'm just keeping that one term. This one has dropped out. Get far enough away, this one becomes small. And in that case, the electric field is easy to solve as well. Excuse me. And the electric field is only transverse. Get far enough away from the source, and things behave the way that you want them to behave. That is, electric field and magnetic field perpendicular to one another, both perpendicular to the propagation direction. So it's a simply propagating way. Because I know the electric field and the magnetic field, it's easy to solve for the Poynting vector. And yeah, I'll write it down. I'll write down. Put it over here, and then I'll erase it again. The Poynting vector is C over 4 pi E cross B. So it's 1 over 4 pi C cubed R cubed R hat. It points away from the source. Second derivative of the dipole moment with respect to time squared sine squared theta, where theta is the angle between the acceleration of the dipole moment, the direction. So let's say if the dipole is just oscillating up and down, then it's very simple. The acceleration is in the same direction as the dipole points, right? So if I just have a dipole doing that, right, my acceleration points in that direction. So that defines the direction for the sine squared, right? And if I make the harmonic approximation, or the harmonic form, so I'll write harmonic here. No, I don't have that expression written down. But I take two derivatives of the dipole moment. There's going to be an omega squared, which comes down out of the derivative. All right? In fact, that's it. I just get a minus omega squared. I'm taking that and I'm squaring it, so it'll turn out that I'll get an omega to the fourth. So if I'm in the harmonic approximation, then this is actually just omega to the fourth P0 squared, where that's the amplitude of the dipole moment of the system, all right? And so the Poynting vector is proportional to the fourth power of the frequency of oscillation of the system for a given dipole moment. And Ohanian has the integral over all angles, which I'm not going to bother doing now. The total output is proportional to the fourth power of the frequency. Yeah.
Is that the magnitude of p double dot squared, or what is,
Oh,
were you squaring?
no, sorry. This thing here, the bracket, means evaluate at t equals r over c.
But it's still a vector, right? Even after you evaluate it as. Because you
Yeah,
crossed it.
do p double dot dot p double dot.
Okay,
Did you follow that?
yes.
It got it with itself.
Okay.
Thank you for asking. Yeah. Okay, am I gonna bother? No. In my notes, my post-it notes, I have the full solution for the center-fed linear dipole antenna. In, let's see, the trick, let me see, what do I want to say about that? Yeah. I won't actually solve the problem. I won't go through it, but let me talk about the physical situation. So what we've got is some source, and then that's going to go out to an antenna, and I'm twiddling these wires upon one another in order to prevent that from radiating, right? So I'm supplying an AC voltage source here, which is going to induce a current in the wire. Yes?
5 minutes.
Oh, okay. Which is going to induce a current in the wire. Now, the current at the end of the wire has got to be 0. And what we're going to end up having here then is a few possible situations. Right? I could have my current look like this as a function. So I plot current along this direction, and at a particular instant in time, I have a lot of current flowing here, and that's sort of busily charging things up. But at the very end of the wire, I have no current. All right? So I have current, which depends upon position. In this problem here, the linear center-fed antenna, we're setting up the current that's driving down the two sides so that they are, so that the maxima are in phase with one another at the middle, right? So my current is a 0 at one instant, right? Then flows and has its greatest flow near the center and drops off to the outside edges. And it looks like a cosine function, right? This is called a half-wave antenna, right? Linear center-fed full-wave antenna. I have to think about how I'm going to draw the pattern for that. But this is the half-wave antenna, right? And it's because we've chosen the length of the wire and the frequency that we're operating at in order to put the maximum here at the center at any given time and the edge at 0. There is a rule here that it's got to be 0. The current's got to be 0 here. Okay? So, but we could drive this antenna at any frequency that we like. It's just that I won't have this pretty pattern with the maximum in the center. Okay. And that's the problem that there we go. I just decided not to solve in front of you. Yeah. All right. I got 3 pages of notes here that I'm skipping. But